So how do we design window functions to obtain higher stop band attenuation? We need to think about two versions for windows, one with even and odd length. So we now analyze a few common types of window. Yeah, we will start with the rectangular window, which is equals to a 1 for n going from 0 to L minus 1, where L is the length of the window. So we can design here our window, a rectangular window with L equals to 16, and we use SciPy signal frec to compute its frequency response. And we have the frequency response here and the normalized frequency from 0 to pi, our magnitude in dB. Here we can observe that its main lobe has a 3 dB width of about 0.05 pi. It's approximately 0.16, and the side lobe attenuation is about minus 15 to minus 25 dB. Oh, we can design different windows which de-emphasize a transition region from the pass band to the stop band and emphasize the stop band attenuation more than the pass band attenuation. So this can be seen as a minimizing weighted squared error function where the parts that we want to emphasize get a higher weight. Well, we can formulate an error function with a weighted square error as follows. Here we have PB and TB are the number of frequency samples in the pass band and the transition band respectively. So here we are defining our error function. In this case we are using 512 frequency samples. Here we have our desired pass band, so we are dividing this number by 4. Here we have our desired transition band, we are dividing this number by 8. Here we are computing this frequency response using frec, and here we are defining our desired frequency response. So we are concatenated ones and then zeros, and we are taking into account the desired pass band and the desired transition band. Here we are computing the weights, so we are giving more emphasis depending on the if we want to emphasize the pass band or the stop band attenuation, de-emphasize the transition region. So in this case here we are multiplying this part here by 1000, and our error will be, we're summing here absolute value of the h, so our frequency response, minus the h desired that we defined here, and we're multiplying by the weights. We can then apply some optimization to obtain the window or filter samples which minimize this error, for instance using SciPy optimize. In this example, a window or filter H, depending on how it's used, of length 16 samples or taps is obtained by this way here. So here we are using from SciPy optimized opt. We pass this error function we defined here. We give this initial values, so it's kind of the guess, the starting point, and then this function will minimize this error function, and we will have here the our window or our filter H. So we get the samples or impulse response, and we plot. We see here. Observe that the negative sign doesn't matter because we only optimize for the magnitude, and the magnitude of the frequency response is given here. We are using frec once again to plot the magnitude in dB. We have our normalized frequency, and here is our magnitude of the frequency response. Observe the decently high stop band attenuation of about minus 80 dB. So usually this optimization gives the best answer for most applications, but there are also more prefabricated windows for filter design with different trade-offs of transition bandwidth and stop band attenuation for convenience.